First live coding session. I hope you're excited. To be honest with you, we're not going to do anything too fancy yet. I just want to make sure that everything is up and running. For this first module, we're still going to introduce the main idea of machine learning engineering, and we are going to introduce the first code to understand the use case we are working in and the data that we're going to have to be dealing with throughout the course. So for now, I don't know where you're watching this, whether it's on YouTube or on Udemy. You should have a pointer that tells you like where to download the material to follow this session. If you're on YouTube, for instance, just check out the comments below the video. You should have a pointer to the Google Drive that contains all of the material for today and for the other courses. If you're on Udemy, you should also head over to the central location where all the material is stored, and you should be able to collect this material from the Google Drive or directly from the Udemy platform. The material that you're going to need for today is, well, first of all, this requirements.txt file, which contains all of the libraries we're going to be using today and throughout the course. You can see that among these libraries is something called Jupyter that's going to allow us to spin up the notebooks and to write some interactive code online. So make sure that this one is in here. And well, when you have downloaded this material from the drive, just make sure that you put it into a location on your local computer that you can access. So for instance, for me, I just created a folder called MLOps, and I just CD'd into this folder. And if you follow the pre-course material setup guide, then you should already have Conda installed on your local machine. And you should be able to do something like conda and list, which is going to list all of the virtual environments that you have access to so that you can build Python software inside of these environments. And for us, we're really looking to build stuff into MLOps. So we're going to be doing something like conda activate MLOps. Things didn't really change much for us because we were already in this environment, but if you were in the base environment, then now you are in this new environment that you created. And then you should be able, like after you've ran the requirements file by doing something like pip install requirements, making sure that obviously you have this requirements file inside of this folder that you have set up for this course. If you do something like this, then now you should have access to this Jupyter library that allows you to spin up a notebook like this one here. I'm just going to head over to the notebooks and the class 1 introduction, which is the one that we're going to be talking about today. And basically what I want to start with is a reminder of what we're going to be building throughout this course. Pretty exciting, very advanced machine learning engineering system, so that we can start having an edge when we play the game of Belote Maniée. Just as a reminder, if you want to get into the game, you can watch some tutorials, you can really understand why this game is so interesting. When you get really good at this game, it's a pretty cool feeling, and then afterwards you can start and move on and play other games like Bridge and things like that. But overall, like what we're going to be doing in this course is we're going to build a model that looks at the cards that are being dealt for you. So for instance, here I have a jack, I have a 9 of spades. These are pretty strong cards. And I want to feed these cards to my model so that my model tells me like, hey, based on what I'm seeing here, you have a pretty high probability of winning this hand, so you should definitely play it. And so the way that we're going to do that is by training our machine learning system on a lot of hands that have been played in the past. And this is what we're going to like check out today. So first of all, before anything, just make sure that you import a bunch of libraries that are going to be useful for this module today. Standard things like pandas, numpy, matplotlib to plot some things. It's going to be very useful to visualize our data. Let's get in a few settings as well so that we can visualize our data frames better. And then obviously here I have set up a bunch of paths. These are pointers to where I'm storing a bunch of things like the data that we're going to be using. So you will see again, like among the material that is shared on the drive is a folder called data that contains all of the data that we need to start and that we're going to be generating throughout the course. So here, just make sure to point this base folder to to wherever you have this data folder and create a new, well, this pointer is automatic, it just takes this base path and then it points to all of the files that we're going to start with and that we're going to be creating throughout the courses. So for now, the only file that we really need is this synthetic data contract. This is pretty poorly named, but you're going to understand why it kind of makes sense that I named it like this. And we're going to go over, let's say, the overview so that we check out the data that we're dealing with. If we do like a very straightforward read of this data, well, that's great. For things that breaks, name error, name path is not defined. Well, that's probably because I talked about it, but I didn't really run this cell here. So if I go back to the read here, then I should have the data read into my data frame. And we can see that it is actually the case. It worked pretty well. So here's the data that we're dealing with. So if you think about it that way, we want to train a model to look at a bunch of cards and tell us whether we are going to win this game or not, so that we can make a decision to play it or not. So obviously what the game is going to need is a lot of reference of past games where it could observe the hand that was dealt and whether we have won it or not, like in the practical sense, whether we actually reach a high score or not. And if you have all of this labeled data that you can feed to your model, then the model can learn from these past hands and can make you recommendations for future hands. It's pretty much the standard supervised learning system that is so powerful for this kind of use cases. And so it should come at no surprise that a big chunk of data that we have access to is pretty much a bunch of previous hands, previous cards that were dealt to a player, along with target variable or some kind of like outcome variable that tells you what happened in the end. And this is exactly what we have, let's say, in this data frame here. We have 500,000 rows of data telling us the contract that was played, the reward or like the outcome that was observed, who started the game, like who started the hand, whose turn it was, the cards that we could see from the player 1's perspective, the cards that could be seen from player 2's perspective, the last player who beat, the visible hand, the value of the hand, a bunch of things that I'm going to talk about. Don't worry too much about the meaning of these guys. Like for now, obviously if you've done the pre-course reading, then you should have somewhat decent understanding of what this means, but I'm going to make sure that this is clear, so don't worry too much about it. But what I really want to emphasize is that we have 500,000 rows containing these hands and the outcome of these hands. And so this is exactly what our model is going to need so that it can learn from the cards that it looks at and come up with a final recommendation of how much points or whether we're going to win this game or not. 500,000 is not a huge amount of data. It should be quite enough to allow us to have a first solution that works decently, but obviously the more data you have, the best it is. That's why machine learning is so powerful. The more data you generate, the less bias you have, and the more robust your solution becomes. And so here, if we really get into the nitty-gritty details of what we're talking about here for this problem, from our perspective, when we play a game, we have access to 12 cards that we can observe from our hand. Card 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. These are 12 cards that we observe and that we have in our hand. And we also observe 4 cards that our opponent has in their hand. What we're going to be doing here is we're going to start very simple. We're just going to take the visible deal. So these are the cards that we see from our perspective in our hand. And we're going to learn from this visible deal to predict the reward, to predict like how much point we're going to score. And so if we start looking at the data that we're dealing with, we see that we have like an average reward of -9, which means that over all of the games that we can study or that we can train on, we have a somewhat small bias here towards losing the game. towards generating -9 points on average against our opponent. So that's not something we should be too worried about, but that's something we're definitely going to come back later, because the central idea of machine learning engineering is that you're very often going to have some data from data scientists that have already kind of like solved a problem and that already are pretty happy with the solution they came up with. But you should challenge everything as a machine learning engineer. Whatever you're looking at, you're not here just to build stuff at scale. You're here to also go back to the solution and make sure that things were done properly. So this is already like a first small red flag. There is definitely like a small bias in the training data, and we're going to see later whether we should be worried about this stuff or not. And interestingly, just as we have a bias towards generating negative value or like just losing on average, we also have a bias towards having the player number one being a starter, like just starting the game. We can see that the starter, like who starts the game, who's the first one to play, is a value that's going to go from 1 to 2. Actually, like if we increase this a little bit, we'll see that the values that we have for starter is 1 or 2. We can make that even more clear by doing something like this. Game data, just get like the starter value and then do something like value counts. And we'll see that we have this tendency to start the game as a small sample bias as well. Like we just have 22,000 samples where we're a starting player. And we have our opponent, player number 2, starting the game just less frequently than we do. And this could already be a reason why we tend to lose on average. But other than that, pretty other interesting things is the starting value of the hand. We usually start with like 60 points in our hand. Again, if you have watched the tutorials to understand the game, you should remember that every card has some points associated with its value, with the jack being 20 points or the knight being 40 points and everything. And so when we talk about here the P1 face value and the P2 face value, we just talk about the number of points that you have starting the game just by virtue of having the cards in your hand, not by having won any tricks or anything. And so that's pretty interesting to look at directly. And another thing that's pretty interesting to look at is our base distributions, right? We can see that in our sample of data, we have a pretty well distributed number of games that are played at tout-à-tout, sans-à-tout, so kind of like all trumps, no trump, spade, diamond, club. You want to make sure that your model is going to learn all the different phases of the game that exist. So seeing that out of the 500,000 games that the model can learn on, can be trained on, he's going to be training on a pretty evenly distributed set of rules that's going to allow him to be pretty well generalized and to be pretty good at beating any human at all of the different system of contracts that there is for the game. In the same manner, what we could be looking at as well is the distribution of the P1 face value, the P2 face value, and the reward. And we can see that our P1 face value is distributed with a small skewedness around the 60 points that we saw earlier. And we can see that the reward has this pretty insane shape. I don't think you've ever seen like a distribution like this. It's a pretty crazy one. We see that the distribution of reward is central around the -9 that we've seen before. And then we generally tend to generate points that are positive and negative within 100 points. So we either win within like 100 points or lose within 100 points. And sometimes, like very often, we can win with a very specific amount of points. We're going to see that later why. And we lose with a specific amount of points. And then in more unlikely games, we win with a huge amount of points, with like 300 points, and we lose with 300 points, which are like definitely training samples that are going to be useful to teach our model. So the first thing that we see here is if we look at exactly the same distribution but in a bit more details. Now we're looking at the same distribution as we were talking here, the distribution of reward, but we look at this distribution of reward from the perspective of the starting position, right? We look at the games where player 1 was the starting player and player 2 was the starting player. So this is the red and the blue thing. And we see that these two are also pretty much evenly distributed. So we're going to make sure that our model is trained on games where player 1 and player 2 were starters and where the reward that we generated in each circumstances is also pretty evenly distributed. So that's going to be very useful to learn about it. Something very cool to look at already is that If we look at the last player to bid on the contract, which is going to be a feature in our model later, if we look at the last bidder of the contract and we look at the distribution, we already see that there is a huge difference in the average expected points when you are the last bidder of the game. We see that when we, player one, are the last bidder of the game, we see that we have on average a pretty negative value that we can expect to win. And when player 2 is the last bidder of the game, we see that we have a pretty positive value that we should win. And so we already see that because we have so different distribution based on this feature, we should already see that last bidder should be a pretty extremely good feature to train our model on. And that's what we see from this graph already. At the end of the day, machine learning is all about finding discriminatory signal from your data. When we have a feature that allows us to find so much discrepancy, so much discrimination in our data, then we know that this feature is going to be very powerful at a later stage. But the one thing that I'm not really like a big fan of very early on, and that's very important to get things straight quickly. One thing that I'm not very a fan of is having a model that, having a training sample of data that has so much unbalanced data with two values here that are so overrepresented that our machine learning model, if it trains, try to predict the reward, it's probably going to be biased towards really predicting this value that it sees here, right? Because it's just so many samples that had this value. I want to make sure that before we move on to feature engineering and training and things like this, I want to make sure that we remove these guys and train our model on clean data. And the way we're going to do it is very simple, like vectorized operation on our data frame. So we're going to start from our synthetic game data, which, if you remember correctly, contains all of the training hands that our model can learn from. And in one of the column, in the column reward, we can see directly all of these weird values that are completely oversampled here. And so what we want to do is some kind of like row operation on this reward column that is going to check every time which row contains these values and rebalance or like remove and filter a few of the rows that are useless here. And so the way we're going to do that is we're going to follow the instructions that we see here in the comment. We're going to keep only the rows where our data is unbalanced. Once we have this unbalanced data, we can follow a pretty similar but like inverted logic so that we keep the balanced data on which we don't want to apply any sampling afterwards. And we're going to apply a sampling method directly on top of this rebalanced data so that we can finally merge the two data frames together, the one where we have all of the balanced data and the one where we have the resampled unbalanced data, or like the rebalanced data as we call it here. So stick with me for this. First of all, we're going to start here, and as I said, we're going to apply some vectorized operation on the reward column, and the way we're going to do that is with a built-in pandas utility that is just accessing the column on which we want to apply the filtering and compare each rows of this column to the thresholds or like the values that we want to filter in or out. So in this case, we're going to keep the values that are above 160 or below 170 because these were exactly the values that we could see in these huge spikes of our sample data. And we're going to apply the same logic to keep the rows that are within this second bound of oversampled data, right? Like so the one that are above minus 170 and below 160. And with this filtering, we have all of the unbalanced data which we want to have for resampling. We can apply exactly the same logic to keep the balanced data, but in this case, the balanced data is just going to be like the reverse of the unbalanced data, so that we know that we don't apply any operations on this data frame there. And then what we want to do is, now that we have the unbalanced data, we want to apply a resampling on it. And pandas provide a pretty convenient method for that. Pandas sample. We can see in the API that If you leverage this method called sample and you provide it either a number of items or some kind of like fraction of how many items you want to keep, then this sample function should be pretty useful to reduce the number of unbalanced data we have, right? We're going to do just that. Here we want to keep 25% of the oversampled data. So we're going to be using the fraction argument of this method, and we're going to be keeping, what is it? Is it like decimal value? What we can see here that they use it as a decimal value, like keep only 50% of the values with like 0.5. So that's what we're going to do here. We're going to keep 25% of our sample data. And once we have these two data frames, the one on which we applied resampling and the one on which we didn't apply resampling, now what we can do is we can merge the two of them. Well, here in this case, it's pretty interesting. Like we don't want to do a merging, we want to do some concatenation or like some kind of union of the two data frames. Pandas again has like pretty decent API for this kind of stuff. So like if we want to do pandas merge or concat, then we can look in the documentation and we can see that very quickly Panda tells us that if you want to concatenate object where you kind of like start with the first data frame and you want to append or concatenate a second data frame, then what you can do is just use pandas.concat. And this is exactly what we see here. Like it's our case where we have two data frames that are very similar in terms of shapes. They have the same column, and we want to put the second data frame appended to the first one to have this kind of result. So we're definitely going to be using this method here. And we're going to replace the three dots by the pd.concat, and we're going to pass it the two data frames that we have. And we're going to run this guy here. Oh, something is not working. Yeah, obviously, like we need to apply the vectorize operation on a specific column. So we're going to run this, and we're going to see the process here where we got our unbalanced data. These are all the unbalanced sample. We kept the balanced data, we rebalanced the unbalanced samples, and then we ended up with final data frame containing all of the rebalanced data on which we're going to learn. And we can see that if we plot this guy now in here, we can see that we have a very neat distribution where most of the unbalanced data that were like here at minus 160 have disappeared because we rebalanced it. And now our model is going to learn on a much more balanced sample of data, which is going to be leading to greater results. This is a reminder that as a machine learning engineer, you're not just someone who builds stuff and scale them and put them in production. You're someone who is data fluent and can understand all of the typical shortcomings that you have from machine learning solutions. And you're like not afraid to go back to your data and to really inspect it and make sure that things were done properly, right? And to take decisions on the way you want to reframe the problem if you think that something hasn't been done correctly. So that was the first live coding session. Obviously, this was not a lot. I just wanted to introduce the use case. I want to show you how we're going to work, right? What we're going to have is we're going to have like live coding like this, where we're going to have instruction that allows us to navigate the code, that allows us to understand what we need to do to improve it. And, you know, a lot of coding is just you really like figuring out how things work and checking out the APIs and stuff like this. So don't worry if things are not too intuitive at first, if it's the first time you've worked with Python, with pandas, on machine learning stuff. All of the things that I do are things that you're going to improve quickly if you persevere and just write a lot of code, right? So don't worry too much about this, and see you for the next coding lesson.